A number is called an irrational number when it is not in the form of p and q, where p and q are integers and q is not equal to 0. Let us look at these examples. So the first example is 3.6 is equal to 18.5. This is a terminating decimal, as we can write this in the form of p and q. The second one says 10.3333 till infinity. 10.3333 till infinity is equal to 31 upon 3. This is a non-terminating figure, but repeating decimal. Therefore, the numbers that can be constructed from the ratios of integers are called rational numbers. Now let us consider a few more examples. So we all know that pi is irrational as it is never ending. 3.14 is the pi value which is non-terminating. So we cannot write this value in the form of p upon q, and hence these kinds of numbers are called irrational numbers. Now let's have a look on revisiting rational numbers. We all know that rational numbers are the numbers which can be written in the form of p upon q, wherein p and q are integers and q is not equal to 0. Let us see the examples now. See, the 25 number can be written as 25 with the denominator 1 but not 0. Next example, 0 upon 1. Here the numerator is 0, not the denominator. The third example says 3 upon 2 and next is 15 upon 3. These numbers are constructed with ratios of integers with non-zero denominations and hence they are called rational numbers. Now we are going to study about a few theorems wherein we will be understanding the theorems and also solving few problems related to them. So now the first theorem says that let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. To prove and solve this theorem is very easy. So that can be written as a square upon p, which will be implied like a upon p. That means if p can divide a square, p will definitely be dividing a also. Let's take a quick example. Let's assume that a square is 25 here and p is equal to 5. Now it is very simple for us to say that 25 can be divided by 5. So let me do the prime factorization of 25, which says 25 is equal to 5 into 5, and hence proved 5 is divisible by the number itself. And hence we can say that if p divides a square, then p will definitely divide a also. Now let us solve an example. This is a very important question for the board exams. The question says that we have to prove that root 2 is an irrational number. So let me just give you a quick tip that says that we have to solve this question with a contradiction approach. What is contradictory approach? As the question says root 2 is irrational, so while we try to solve the question, we will assume in the starting only that root 2 is a rational number. And as it when we'll proceed further, we'll get a contradiction which says root 2 can never be rational. Let's solve this question now. Now let us square both the sides. So root 2 whole square is equal to p upon q whole square. After squaring the sides we get 2 is equal to p square upon q square. Q square is equal to p square upon 2, and therefore p square can be divided by the number 2. Now according to the last theorem which we have just studied, if p square is divided by 2, then p will definitely be divided by 2. Hence it is proved that we can write p is equal to 2m. Now let's give this equation a name. So let's give it a number 1 and we'll move further. Now let us put the values in the equation which we have written above. Q square is equal to p square upon 2. Let's put the values now. As we know, p is equal to 2m according to the first statement. Q square becomes 2m whole square upon 2. Then q square is equal to 4m square upon 2, and we can cancel the 4 and 2 and we get 2 in the numerator, and hence m square is equal to q square upon 2. And see the magic, again the q square now is divided by 2, which proves that q will also be divided by 2. But if you remember, just before some time we have assumed that p and q both are co-primes, that is the HCF which they are having is 1. But here we have proved with both of these statements that they both are divisible by 2. So how is it possible? Hence it is proved that our assumption is wrong and root 2 is not a rational number but an irrational number. Now let's quickly go on to the next question. The next question says that show that 5 minus root 3 is an irrational number. Now the contradictory approach will actually not solve your problem. So we have to assume here that root 3 is irrational. Alright, now let's start solving the question here. The approach which we are going to follow in this question says that all the irrational numbers have to be written on the left hand side and rest everything will go on to the right hand side. Alright. Now let us assume that 5 minus root 3 is a rational number. Therefore, we can write it in the form of P upon Q. Now my approach says that if I write it in this form, then root 3 is equal to P upon Q minus 5. Now we see that all these three numbers or variables, that is P, Q and 5, are integers. So this side is rational, that is the right hand side. And we know that root 3 is irrational, so how can they be equal? Therefore, the right hand side is rational, but root 3 had to be irrational. Hence, the assumption that root 3 is a rational number goes wrong, and hence 5 minus root 3 is an irrational number. Now let's take a quick review of how do we solve this question, the approach which we have to keep in our minds. The approach says that root 3 is irrational, but you see that right hand side will be proved irrational and therefore the contradiction comes in the picture and hence we prove our theorem. Now the next question can easily be solved by you yourself, but we'll just solve it together for a better understanding. So the question says that show that 3 root 2 is irrational. Again, we follow the same approach which we have just followed in the last question. The solution says that let's assume 3 root 2 is rational. Alright, therefore 3 root 2 is in the form of P upon Q. Therefore 3 upon root 2 is in the form of P upon Q, that is 3 root 2 is equal to P upon Q. Now root 2 should be on the left hand side as all the irrational numbers have to be on the left hand side. So I write root 2 is equal to P upon 3Q. Now I know that P and Q are integers. Therefore the right hand side is rational now. Again, our assumption goes wrong and hence we prove that 3 root 2 is irrational. Now what we are going to discuss next is that whether the decimal expansion of any number is terminating or not. So before we go on to the result, let's consider a few examples and see what is a terminating expansion and what is a non-terminating one. Now let us consider the decimal expansion of these numbers. So we are dividing 5.0 with 8. So the answer is 0.625, but when I come down, I see that the remainder is 0 here. So what is meant by the remainder being 0? It simply means that the decimal expansion terminates here. See the second example. In the second example, we are dividing 50 by 32 and again, there is no remainder left in the end. That means this number is also having a decimal expansion which terminates at the end. That implies that when r, that is remainder, becomes 0, the decimal expansion of my number terminates. So now here we are dividing 2.0 with 9. The remainder in the end is 2, which will again be converted as a divisor and we'll keep on dividing the sum until r becomes 0. But as we can see, remainder in this kind of examples never comes to 0. So what does it mean? It means that the remainder ultimately terminates. It is a non-terminating but repeating example. In the another kind of example, we are dividing 20 by 11. And here also the remainder will never become 0, but there's a small difference in this example. There is a complete block of digits which is getting repeated. So as we know, it is 0.18. So the answer becomes 0.181818 till infinity. So that means the 18 is a complete block which is getting repeated again and again. Now what do we observe in all these examples? We observe that the decimal expansion of a rational number is either terminating or non-terminating. But how do we come on to the result of the same? Alright, so let us discuss it result by result. So the result one says that let x is equal to p upon q be a rational number such that prime factorization of q, that is the denominator, is only of the form 2n 5m, alright, then the decimal expansion of x is terminating. How? I'll just tell you that. That means 2n 5m states that in denominator, that is in the case with the q integer, it should be ending either with 2 or with 5 or with both 2 and 5, or because as we multiply 2 and 5 it becomes 10, so it should be either ending with 0. But the denominator to end with 2, 5 or both of them or 0, what do we have to do? So how do we come to this result? This is the question which persists. Alright, so now let's check how do we come on to this result. So my next example says that 2 upon 25, and we have to check whether this fraction is terminating or non-terminating. So let me just do the prime factorization of 25, which says 2 upon 5 into 5. So 2 upon 25 can be written as 2 upon 5 into 5 also, and the same can be written as 2 upon 5 square. So now if you see in the denominator I already have 5. If I convert this into such a number which gives me the ending number 0, I'll be able to solve my question. So 5 square means the ending number will be 5. What if I multiply it with a common number? So 2 square will be multiplied with both the numerator and the denominator, and it becomes 2 into 2 square upon 5 square into 2 square. But why 2 square? Why not any other common number? Because I had to get the digit 0, and after I had 5 square, I had only one option left, that is 2 square. So if I multiply the 5 square and 2 square, I will definitely get a 0. So we got the fraction which says 8 upon 10 square, or 8 upon 100, or the decimal expansion says 0.08. So what you have to notice here is that if the denominator is in the form of digits ending with 0, it may be 10, 100 or 1000 or maybe more, what happens is that my fraction, I know, will definitely going to terminate. The second example says 13 upon 125, which I can also write as 13 upon 5 cube. Again, what is the case here? The ending number is 5. What is missing here? 5 is missing. Yes. So what if I multiply 5 cube with both the numerator and the denominator? Yes, my fraction becomes 13 into 5 cube upon 2 cube into 5 cube. That gives me a fraction which says 104 upon 10 cube. And the decimal expansion which writes as 0.104. So this is how we convert the rational numbers which are in the form of p upon q, wherein q is in the form of 2n 5m, to an equivalent rational number of a by b form, wherein b is a power of 10. Now let us take another example wherein we will be dividing 1 by 7. Now you have to notice here that the denominator 7 is clearly not in the form of 2n 5m. Had it been in this form, the ending digits would have been either 2 or 5 or 0, but this is 7. It clearly says that it is not in the form of 2n 5m. Hence, as you can see the division also, hence 0 is not showing up as a remainder, and r will start repeating after a certain stage. As you can see, after 3 it has started repeating starting from 7. So we have a block of digits, namely 1, 4, 2, 8, 5, 7, which is repeating in the quotient of 1 upon 7. Fractions will never have a terminating decimal expansion. And hence we come back to the theorem which says that let x is equal to p upon q, where p and q are co-primes, be a rational number such that prime factorization of the denominator, that is q here, is not of 2n 5m form, where n, m are non-negative integers, and then it has a decimal expansion which is non-terminating repeating. And hence we prove that decimal expansion of every rational number is either terminating or non-terminating. To check your understanding or learning of the concept, go to our practice tests. Thank you for watching the video.